All right, thank you all for being here. So to begin, GNSS stands for Global Navigation Satellite Systems, and that is all the positioning satellites in space. This compares to GPS, which are only the US operated satellites. So this system is composed of 3 components. Number 1 is the satellites in space. Number 2, the control, and that's the worldwide stations that monitor the condition and orbits of these satellites. And then 3, that's the user, which are the satellite receivers. So this system is compatible with RTK. RTK means real-time kinematic surveying, which basically means solutions in real time. The setup for RTK involves 2 receivers, the stationary base and the moving rover. Both are typically set up on bipods as seen in the picture. So the stationary base communicates with the satellites in space, and it also acts as a reference station with a known precise location. It calculates corrections, and then it sends these corrections to our moving rover, giving our rover the capability of receiving on-the-fly solutions up to 1 centimeter accuracy. So the objective of Project Bullseye was to test the accuracy and the precision of 4 different receivers that UNAVCO distributes to its community for scientific research. These include the StoneX, the MLID, the Trimble, and the Septentrio. So we took these accuracies and precisions and made comparisons amongst the units. And for accuracy, we're testing how close our data points can come to the true value, aka our static point. And for precision, we're testing to see how repeatable these data. And also, as advertised, these units can yield centimeter accurate solutions. So part of this is to make sure that that is indeed true. So the goals and significance of our project was to create a reference guide to help aid scientists when selecting the receiver that best suits their research project. We also wanted to make an instrument evaluation reference for UNAVCO to use for their receivers. So in order to test our units over a distance, our research spanned from Boulder Reservoir to Coot Lake to North 55th Street. By doing so, we achieved a distance of 2 miles. We then decided to take this 2 miles, divide it into 11 interval points, each being 0.2 miles apart from each other, with the addition of mile 1.5. So our base station is indicated by the white circle at Boulder Reservoir. So in order to expand this distance, we went over to Lookout Road and we achieved 3 miles. So now we have 12 areas total that we're surveying. And at each of these 12 areas, we have mag nails in the ground. And mag nails are basically just nails with a little divot on the top. So that way, each time we went out with a receiver, we were putting it in the same exact spot for consistency. So to begin our data collection, we started with our static points. Our base station had an occupation of 3 hours, giving it a very precise location. And our 12 interval points had 30-minute occupations, also making them precise locations that we could then compare our RTK data to. So to test our units for accuracy, at each of these 12 areas, we had a central point. At each central point, we took 10 data points, calculated out an average, so that way we're pulling our average from a big pool of data. And then the question came up, does accuracy change over a longer duration of time? Well, to answer this, at each of the central points, we also performed control points. These control 60 seconds. And this compares to our central points, which only took 1 point over 1 second. So that took care of accuracy. And to test for precision of these units, at each of those 12 areas, we also had 3 cluster points. And these are the 3 nails up top right here. They're set at about 2 centimeters apart from each other. And this helped answer the question, can these units in fact yield centimeter precision? And with that, I will hand it over to Kai.
Thank you, Taryn, for that lovely introduction. So I will now be going over the results of our project. And considering we collected over 1,500 points across various types, we had to make sense of it through a series of spreadsheets and graphs. Some notes going forward to understand our graphs, I'll be referring to error as root mean squared, which essentially represents the spread of error within a set of numbers. Also on the axes, error is usually represented in meters. So when we're talking about error, these are fairly small. We're talking sub-centimeter to centimeter at most. So this particular graph shows central points error measured over distance, particularly what the instruments report as their error versus what we calculated through standard deviation from that central point using that static occupation, which is our most accurate solution. So some things to note here is that we see an increase of error across all devices around the 2,500 meter mark, and we believe that was due to obstacles. And also it's interesting here that generally speaking, that our calculated standard deviation is much more precise than what the devices report. So essentially the devices are far more conservative when they're reporting their accuracy. Next slide, please. So this graph shows our central versus control. So recall that our central is one measurement, whereas control points are 60 measurements averaged into a single point. The dashed lines represent the central points, whereas the solid lines represent the control points. So some things that are interesting here is that the control MLID data actually increased in error as we got further out, which we are unsure why, compared to the central point. So that kind of goes against the theory of the control points being more accurate. However, the rest of the points you see are usually the control is far more accurate than the central points, especially in the case of the septentrio. The septentrio control points were essentially almost 0 in terms of error. So that was also quite interesting. The Trimble R7, unfortunately, the control point stopped recording at around that 2,500 meter mark due to poor connectivity. So we weren't able to collect the rest of that data. The MLID also has an interesting spike near that 2,500 meter mark in the horizontal RMS. Not sure why particularly the MLID spiked around there other than those obstacles and why it spiked so much compared to the others. Next slide, please. So here we see a visual representation of essentially how accurate those points were. The size of these dots represent the horizontal error. We're comparing all of these devices as well as the central and control points, so there's two different types of recordings, to the static point. The static point, again, is our most accurate solution where it had a base occupation of 30 minutes. So everything is in comparison to that. And so looking at this, we can see at 0.2, errors are quite small across most devices, except for the MLID, which does have a larger error margin than the rest of the devices. And most devices are recording basically on top of that static point. So it's fairly accurate. And then if you look to the right, actually, we see very similar data, which is interesting to us because essentially our hypothesis going in is as we move further away from the base, the rovers would essentially become more and more inaccurate. But as you can see, most of the devices are recording pretty much still on top of that static point. The only exception to both of these graphs is the Stone X. They are both off by the central and control points are off by several centimeters. We believe this is due to internal miscalibration of the leveling device inside the machine. So that unfortunately threw off all of the data. Something also interesting is that you see that septentrio is quite accurate in terms of the size. Those orange dots represent the septentrio, and you can see they're quite small in comparison to the rest. Next slide, please. So in our conclusion, we created a qualitative analysis of these devices based on our use. The septentrio did rank top just due to those small margins of error. The Stone X was next. It had smaller margins of error. Unfortunately, that internal miscalibration of the leveling did throw off data, but we believe if it weren't for that, it would rank quite well. The MLID was next because it had a fairly large error set, and unfortunately, that would kind of disqualify it from being of a decent choice for scientists who need extremely precise measurements. And then the Trimble R7 was on the bottom because it had fairly large errors and definitely increased over distance. This is due to it being some of UNAVCO's oldest equipment, roughly like 20 years old, and can only see GPS satellites. So we believe that this could be phased out of their equipment pool. Future work is scientists investigating more about error over longer distances. So basically going past that 3-mile mark and seeing if error will start increasing more exponentially at that point. Also seeing how obstacles affect data and a quantitative analysis. So essentially like how trees and all that affect the radio link as well as the sky view of the receivers themselves. Implications of the project: scientists aided by UNAVCO and funded by the NSF can use this published data to choose a device that suits their needs for their research project. And UNAVCO can use this data to determine if their equipment is worthwhile to upgrade. Next slide. And these are our acknowledgements. Thank you. Any questions?
Fantastic. Glenn, you have a question?
Yes.
I think it's more of a comment than a question, but very nice job, nice work, nice research study overall. My one comment was you took 30 minutes of data on your reference point, which you're calling your static observation with the highest level of precision. And then was that data collected very close in time to when you did the RTK study? Because obviously the static position is going to also vary as a function of time during the course of the day, and even at longer time periods than that.
That is true. Like things like the clouds can affect, like the weather can affect how the data is collected. But our static points, we recorded those on a separate day from our RTK points. So our procedure, 2 days collecting the static points, and then the following weeks, we were basically averaging 2 instruments a week. So there were different variations of weather patterns out there, which is important to note.
So you basically use the same static data to define the position of the base station throughout all of the other studies when you did the RTK?
Correct, yes.
Okay, thank you.
Mm-hmm.
Thanks, Glenn. So there's a couple of questions in the chat. Really quick, did you only test a single antenna of each type? The StoneX might have a badly calibrated phase center that varies between individual antennas.
So we did not use the single antenna like across measurements, I suppose, which could affect that. So essentially when we were recording both static and RTK points, we were using separate devices. So essentially they usually come in kits of 2. And we were alternating between 2 kits, so that could impact data theoretically. If that answers your question.
Great. And then we have someone wondering how to get a hold of the written report.
So we're going to be finalizing a report here soon, and then hopefully our mentor Marianne Okel will be working to put a summary of it on the UNAFCO website. So hopefully you'll be able to see it there. Or if you want more detail, perhaps we could email to you directly.
Great, got a couple more questions. All right, how did the weather change during the collection of the data? Do you have a photo at each point, particularly the 2,500 meter point?
So we don't have photos of all of our data points. We did take notes when some days were particularly windy. Like when we were out there July 1st with the StoneX, it was a windy day. The weather, like some days, most days are actually really nice, clear skies, sunny. There were a couple days where the clouds rolled in later in the afternoon, and it never rained while we were collecting our data, but there was cloud cover.
Okay, great. Last question. Says, I wondered what the obstacles were. You mentioned trees. Were those the obstacles, or if not, what were they?
So
yes.
yeah.
Oh, sorry, Kai, go ahead.
Okay. Yeah, so the obstacles we're referring are usually, in our case at least, trees or other flora and fauna, that sort of thing. So near Coot Lake, which is where we took some of those 2,500 meter points, there was a lot of trees that could be blocking basically our radio link. So there was trees in between basically where the base is and where our rover was recording. So that could interfere with the communication between those two. And also the obstacles essentially can, depending on where they're located, and if they're near the rover where they're recording, it can block the sky view of the receiver, which essentially blocks it from seeing more satellites, which could also impact quality of data.